So, hello everyone. It's about time that we start with this webinar. I hope you can see my slides already. If you have any questions during this presentation, please feel free to use the chat tool or the Q&A session provided by Zoom. I will try to answer all the questions that you have after the presentation. So, glad that you joined me for our first online ArangoDB meetup. And I would just like to start with a general introduction to the technology that we provide and the multi-model data approach that we have. So first of all, a little bit about myself. My name is Michael. I'm working for ArangoDB since the beginning. And right now I'm the responsible for all the graph features that we have in the database. Good. So now let's get started into the talk. First of all, what do we mean by our multi-model approach for new generation databases? First of all, in the history, we always had these single model databases, the relational databases, where we just had the database completely separate from the application logic. So no matter how the data model in your application looked like, you actually normalized it and just tried to force it into the general relational database format, which in most cases ended up with a pretty complex, pretty ugly, and not handleable data format in a lot of those cases. So this screenshot that we have here is one of our customers who just came to us with this and said, okay, I can't work on this data model anymore. Could you please help us? And as these problems arise, there was a new movement in this area. But first of all, with the relational world, of course, we can solve a lot of problems, pretty much all of them, but it's not always the best way. So in my use case that I would like to present in my presentation here, an e-commerce system, we can do it in a relational world. So we'll have like 5 major categories. On the top left, we have a sales history, which is quite simple. It just states which product has been bought by which person. On the bottom left, we have a shopping cart, which just contains the information that the current user has added in the cart to buy later on. On the bottom right, we have the product catalog, which essentially has one central table with all the shared information. So the product ID, probably the price, so the information that every product has. And then the schema actually explodes because most of your products just have a little bit different attributes. And if you normalize them properly, you always have to create a separate table for all these different attributes. On the top right corner, we have the customers, which are okay in one table as long as you sell for one country only. But as soon as you sell for more than one country, you have different address or name formats, and then it suddenly gets very, very complicated to store these information. And on top in the center, we have recommendations. Recommendations are pretty easy to store because they are just many-to-many relations. One user has bought some product, but the thing with recommendation is how you actually query them, because you want to find other products that are somehow related to the products that you have already bought. And this is hard to formulate in a relational world. And to overcome these issues, there actually was a new movement for databases, the so-called NoSQL movement. And we call this is the multi-model era because we use different database technologies for different data formats that we have in our application. And the 3 major players that we have here are JSON document stores, graph databases, and key value stores. A JSON document store is typically based on the key value store. All documents have a unique identifier, and then they store JSON documents by this identifier. They can group documents with logical similarity in so-called collections, pretty much similar to relational world tables. These documents are attribute structured and they are schema-less. So that means you do not tell the database beforehand, in this collection, every document will have an attribute name and it will always be a string. you just store attributes in it, and if one of them doesn't have a name, the database doesn't really care. In addition, you get queries and indexing of those document attributes. So you can actually find all documents that have identical names in the database pretty fast. Next major player, graph databases. Those focus on many-to-many relations. So in the document stores, you typically do not have something like joins, so you do not have relations at all. The idea is to denormalize everything, and everything that you need at once is just put in the same document. Graph databases do typically vice versa, so they try to normalize as much as possible, and they want to convey the complete information alongside the relations between the entities that they have. Graph databases typically store property graphs. That means on each vertex in the graph, you can have arbitrary attributes, and also on the edges, you can have arbitrary attributes. And then you can search for something where the document, the vertex, has certain features, is connected to other vertices having certain features, where the connection has certain features as well. So pretty complex queries. And the sweet spot of graph databases is if you query for passes of variable lengths. So if you say, I am connected to someone else, but I do not know how many people are in between there. Or if I say I buy a train ticket at one station, and this train ticket allows me to go for up to 6 stations, where can I actually get? Which is pretty hard to formulate in a relational query. And the last major player are key value stores, the easiest database format that you could think of, because key value stores just map one unique key to something which they call data. They do not treat anything in the data, so the data is fully opaque to the database. And you can only get this piece of data back by its key. You do not have complex queries or something. But therefore, key value stores are extremely fast because they're super simple. And they pretty much scale endlessly because you just have to distribute evenly all the keys that you have, and then by some clever hashing, find out which key is actually stored on which server that you have in your database cluster. But now you have to think of, okay, now I have my application, I have my logic in there, I need some data formats. What is the right database that I have to use? And this forms the term of polyglot modeling or polyglot persistence as named by Martin Fowler. And now I'll give you some rules of thumb where you just can pick the right data stores for your data. So first of all, if you have some structured data, so you have data where you know there are some certain attributes in it and that you want to query for it, but this structure is flexible. So some documents have this kind of structure, some have a slightly different structure and so on, or even mutable. So in the first year, you just store 3 attributes, and then you change something, you have to store 4 or 5 or 6 attributes. Then you are best off by taking a document store, because document stores are designed for this schema changes in mind. You can just update on the fly a new schema in the database without using this alter table approach. If you had a lot of many-to-many relations and you want to query by arbitrary many steps between those entities, or even by unknown path lengths, then you're actually best off with a graph database. Those are designed for these types of queries. If you do not want to manage any complex data, but you're fine with only key lookups, then you're best off with the key value store, because you do not have complex queries at all. You just want to store something, for example, the session ID, and then get the session information back by this ID. And you do not want to find out, okay, which sessions share certain features. But in many, many cases, you actually have a mix of those. So you have somewhere some structured data, some flexible data model, then some relations somewhere, and probably something that would be best done with a key value store. So in this case, you typically end up with having all the 3 data stores that you need to do the best thing for your application. Now let's talk again about the use case for the e-commerce system using single model databases. What we first have to do is we have to check out our application and divide it into the different parts of application data that we need. We have already done that in the relational slide before. So we have 5 major players: the sales history, the shopping cart, product catalog, customers, and recommendations. Shopping cart is the easiest thing because typically we do not care for similar shopping carts or for content in a specific shopping cart. We just want to have the session ID from the user and want to find the shopping cart that belongs to this user. So for this part, key value store would be the best choice. Sales history typically needs to store some more complex things and we want to find out some information. So there we should use a document store because we want to actually query the attributes there. For product catalog, document stores are for sure the best choice because the schema between different products just differs slightly and has a lot of information in common. And this is where document stores are specifically designed for. So you can just make one product collection and store all the products in this one place without caring for the little differences between them. For a customer, the same holds true. So having different countries where you ship to, we are having slightly different schemata for different addresses, different names, and so on and so on. And this is also the perfect use case for a document store. For the recommendations, you actually have relations between customers and products. So relations sounds for a graph database. So now we have identified that we need at 3 points a document store, at 1 point a key value store, and at the last point a graph store. And now we can follow the polyglot persistent approach that Martin Fowler suggests and just focus on each of them separately without looking left and right and try to find the best technology that solves this problem one by one. And if we do so, it is possible that we just decide to pick 5 different technologies just to solve this simple e-commerce system problem. Because in the certain use cases that we use in the different places, one technology might have the one feature that is a little bit better than the other technology, and therefore we should use it in this case. What are the benefits that we get out of this, and what is the overhead that we actually have to pay? So the benefit is we have a natural mapping of the application data directly into the database. So typically, if we have semi-structured data in our application in some more or less JSON format, we can just take it and throw it at the database and it will store it without any denormalization and stuff that we have to do manually. Furthermore, the database is optimized for this exact data format. So we're not forcing anything into a database that is not designed for it. Also, you get the queries tailored for this data format. So for a graph database, you get graph queries. For a document store, you get document queries. For a key value store, you get key value queries. And you do not get like some document queries which you have to transform to actually query a graph with it, which doesn't work very, very well. And the benefit for a developer is that he or she can focus on writing the business logic and do not have to transform the data format from the application into the database and vice versa. What is the overhead that we have to pay? First of all, at some points, the data has to be stored redundantly and has to be kept in sync. Let's recall the recommendations. Recommendations actually connect customers and products. And in order to query them, we have to travel alongside the path of those recommendations or these bought history. And we would need some information from the customers and some information from the products. So for example, we want to filter by similarity of the product or by the price. So therefore, this information has to be replicated from the product catalog, which is stored in a document store, into the graph store, which is holding the information for recommendations. And there is no tool that I know of that actually does this syncing automatically. So this would be on your side to develop. Next overhead that we have to pay is there are several technologies involved. So in this simple e-commerce example, we are already using 5 different databases. Someone has to manage them. Someone has to learn all the different query languages. And of course, no software is bug-free, so you have to live with the bugs of 5 different technologies. And of course, administration of this whole thing is a huge effort. And now comes the question into mind, is there a possibility that we can get the benefits without having to pay for all the complete overhead? So is there some kind of shortcut? And the answer is yes. Right now, they are emerging a lot more than in the couple of years, in the last couple of years. So they are emerging so-called multi-model databases. Multi-model databases can store several data models. Typically, they can store key-value pairs, documents, and graphs inside the same technology because these 3 fit very, very well together. Documents are based on key-value stores, so those just go along the lines. And if you now allow to connect those documents by relations, you can actually allow for graph features using the same technologies. Furthermore, multi-model databases deliver query mechanisms for all the given 3 data models, so that you just can use a multi-model database only as a key-value store, or only as a document store, or only as a graph store, or as something that mixes everything. You get everything for all the 3 data models that you need. If we now go back to the use case, again, we split it up into these 5 sections. Again, we figure out 3 document stores, 1 graph store, 1 key-value store. But now we actually take a look left and right and see, yeah, 3 times document store, okay, we could use the same thing. A graph store, a key-value store. So if we just use 1 multi-model database, can actually cover all of these 5 data models. Doesn't mean that it has to be a single instance. You can still store them in separate instances if you want to, if you need some separation of concerns. But the benefit is you just have 1 technology that can actually cover all the data models at once. So let's take a look again at the benefits and the overhead. On the benefit side, we still have native mapping of data into the database. Database is still optimized for those formats. You get the queries tailored for those formats, so you can still focus on writing the business logic. The overhead, and there something changes. So the data has to be stored redundantly and has to be kept in sync. Actually not, because we can just store it in the same instance, and then syncing is because we just use the same physical data. Several technologies involved, also not true anymore. We just need 1 multi-model database. And therefore the administration is really, really simple in comparison to having a lot of different technologies aboard. So we can actually change this slide to having another benefit. We just have 1 technology involved in our complete stack, which is nice. And now let's dive a little bit deeper into ArangoDB. And I would like to do so by presenting my 4 favorite features of ArangoDB. So first of all, it offers AQL, which is the query language, having joins and traversals all in the same technology. So you can just combine them in arbitrary ways. Furthermore, ArangoDB is ACID, including multi-collection transactions. So a guarantee that you typically do not get from document stores. And of course, ArangoDB is a multi-model database, stores graphs, documents, and key-value pairs. And the 4th thing is something that is not related to a database per se, and that is called Foxx, which is a framework that allows to extend the API of the database and adapt it to your needs. Good. Next section of my presentation. Let's do a short introduction into ArangoDB query language by comparing it to SQL, which I assume that most of you actually know. First of all, let's talk a bit about the terminology that we use. On the left-hand side, we will always have the SQL equivalent, and on the right-hand side, we will always have the AQL equivalent. In both technologies, we actually have databases, so groups that store large amounts of data into one huge chunks. Then in the relational world, we have tables. Tables group logically similar documents together into one place where you can store them. So for example, users table stores all the users. In AQL or in ArangoDB terminology, we use the term collections, which allows to store logically similar documents in one place. Inside a table, you typically have one row, which is one data information. And this row is in ArangoDB called a document because it's one JSON document inside a collection. Then inside these rows, you typically have different columns where you actually have the real data. So one column for name, one column for the age, and so on and so on. In ArangoDB, you have attributes inside the documents, one attribute for name, one attribute for age. And you can also have nested attributes. So within an attribute, you could store another document if you like. In relational world, you can join across tables. In ArangoDB, you can join across collections. And then now we have the same terminology, a primary key that you can define on any table in a relational database. In ArangoDB, you always get a primary key, which is called _p on every collection. And of course, you can define additional indices on top of the collections or the tables. Now let's start diving into the real query language. Again, on the left-hand side, we have SQL. On the right-hand side, we have AQL. Simplest query, select star from users. And there is already the first difference. In relational queries, you first say, okay, this is the information that I'm interested in. Star means everything. And then you say where you find it. In AQL, you typically have this for loops where you just say, okay, I want to go over the users collection and store everything that I find into this variable user, and then return everything that I have stored into this variable. So the result of those queries would be the same. Of course, we can also do projections, so only select parts of the data. So select name from users is identical to for user in users, return user.name, because that will access the name attribute from every user object that it has found. Note here, in both cases, you do not say, oh, please database use an index for one or the other. If you have defined an index on the name attribute, the database will figure it out and use it for performance. Furthermore, you can define filter conditions or where clauses. In a relational world, you typically just select from something and then define where this or that has to be true. In AQL, you have more the streaming way, where you just say for user in users, filter user.active is equal to 1, and then return user.name. And again, the filter will figure out if there is an index available or not. So now we could query the data. How can we modify it? And this is pretty similar in both cases. So if you want to update something, in a relational world, we just say, please update the users table and set the following column to the certain value where certain condition is true. In ArangoDB, you just say, update something by primary key, for example, with the new value that you want to add in the given collection that you want to change. Delete pretty much is the same. So in SQL, delete from users where some conditions are true. In AQL, you just do this looping again. So for users in users, filter all the users you want to delete, and then remove the user in users. And of course, we can also insert documents. So it's just insert some JSON into some collection in AQL. As this is a bit boring, I will just show you live how this actually works. Therefore, I have started an ArangoDB instance, fresh and empty. So this is the ArangoDB web interface. And I will just add a new collection in here. Let's say my collection. Save. Everything I have to do, now I got an empty collection, which has nothing stored in it. Then I will go to the Queries tab, and I will just try to insert something into this collection. So insert foobar into my collection. Execute, and it actually did write something. You can figure it out if you just say for x in my collection, return x. And we should end up with something that has foobar stored in it. We can also do some loops in AQL. So for value in 1 to 100, which will just fill the variable value with all the elements between 1 and 100. Insert value into my collection. So this has executed 100 writes, and if you just return it again, we'll just figure out that we now have 101 elements having increasing value operations. And also we can just filter them. So x.val is equal to 24, execute, and we will just find one of those elements as supposed by the filtering condition. One useful tool that we have is the so-called explainer, which allows to explain what the database actually has to do when it tries to execute the query. And this will just take the query string and will tell you which it has to do. So in this case, it has to do a full collection scan, going over the entire collection, executing the filter condition, and then just returning the result. Full collection scans are like full table scans, extremely expensive. So we would like to reduce those. And we can do so by just defining indices on top of the collection. So we just go to the collection tab, go to indices, and just say, please add an additional index. We have 5 different indices available: geo index for geo coordinates, full text index for full text searches. And then we have a hash index and 2 sorted indexes, a persistent and a skip list index. So for now, we are fine with the hash index on the attribute val, and we'll just create it. And if we now go back to this query, explain it again, it will just say, oh, I could do a hash index scan, which has a selectivity of 100% because I just have unique values in there. And therefore the query will be way faster than the one that I've just executed. You won't see any difference because I do not have a sufficient data amount inside my database here. So let's go back to the slides. Next important thing that you often need is so-called aggregation. So just counting or grouping something together, which looks a bit more complicated in AQL, but it actually is more powerful. So we have a very complex documentation about the collect keyword that we have in AQL available. So basically, select gender and count star as number from users, group by gender, could be translated into collect gender is equal to one attribute on the user with count into number. So that means all distinct gender values will be collected into the variable gender, and number will then contain the amount of genders that we have. And then we can just return gender and number, and we can just figure out how many female and male persons we have stored in our database. I promised that AQL can do joins. So we do not have the join keyword, we have something else. So in a SQL, you just do select stuff from users inner join with friends on certain conditions. In AQL, you just trigger 2 for loops. So one going over the users collection, the other one going over the friends collection. And then you just say filter where these attributes are equal. So pretty much the same condition that you would write in the on statement for an inner join in a relational world. And then you can just return it. And this will actually have the same result in both databases. Also, you can do outer joins. So an inner join will only return something if there is a match on both sides. Outer join, and in Arango we only have left outer joins. You can also return something where you do not have a match on the second table or collection. So the outer join here is you again iterate over all the users you want to join, and then you can just return something with a subquery, which just starts a new query going over the friends and checking for where the friend user is equal to the users underscore key. And the result will then be an object containing a user and all his friends. Good. Next section of the presentation. The last thing that was on my slide, which is called Foxx. And Foxx is a nice framework that allows you to turn your database into a kind of microservice. So the idea is that Foxx allows to add a customized and versioned REST API, which is completely integrated into the database. It is written in JavaScript, and it allows to ship an administration front end with it. In order to ease your developing experience with Foxx, we have included authentication mechanisms, namely OAuth 2 and HTTP basic auth, which allows you to expose the Foxx API to the outside world and allow users to set up their accounts connecting to the Foxx API, which are different from the database accounts. So you do not give them root access, you just give them access to everything you have defined in the Foxx microservice. And only this code will be executed in the user space. They will not get full access to everything with their user. And use cases that we had in mind when designing the Foxx framework are multi-device setups. Because in multi-device setups, you typically have different programming languages on the different devices. And if you talk with them directly with the database, that means you would have to write down the query mechanisms, the parsing, and everything for each device differently, and again and again and again. With Foxx, you can just do this one parsing, expose an HTTP endpoint, and every programming language for these devices can typically connect to an HTTP endpoint and just receive some JSON. And therefore, it's pretty easy to just write this Foxx service, write the JSON receiver on the devices, and you're already done. Same holds true for microservice architectures. So they typically talk to each other via HTTP. And if you just say the database is just another microservice, which has an endpoint which you can connect, then the whole area of all the other microservices doesn't need to know that you're actually using a database, that you're actually using ArangoDB, and that you're using AQL. They don't care. They just have an HTTP endpoint where they can fill in the parameters, and that's it. And this gives you lots and lots of possibilities of database abstraction to actually make your complete application unaware of that it is actually talking to an ArangoDB instance or even a cluster of ArangoDB instances. It doesn't need to know because it just talks to this Foxx endpoint and that's it. So what is the general concept that we had in mind? So first of all, the idea was to have data-intensive operations on server side. So we do not want to have the full business logic that does like super heavy computation inside the database, but we want to have everything that just does some data operations, some data aggregations, probably several queries, transactions, and so on. That should be done directly into the database, and the complex business logic should be outside. In order to get that, you will have fast data access. So whenever you are inside a Foxx service, you get raw access to all the data that is stored. And the Foxx service is just a thin layer around the database. And you can combine several queries inside a route. So the use case that we have, for example, is you have a fast query that returns some documents that you want to present the user. So for example, this recommendations, please look at this or that as well. But you always want to present like 10 items to the user. And the fast query probably just returns less than 10 items. If you now go a round trip, so asking the database for the fast query just returns 3 items to your front end, you'll actually have to ask again, oh, please give me 7 more and do a slower query. If you encapsulate it in a Foxx service, the service already can figure out, oh, the first query just gave 3 results. I just directly execute the long running query because you need that anyways. And then I will give you 10 results back in one go. So you just have one call to the database and you get both queries executed if necessary or not. Furthermore, the idea is that the database is just another service. So your application doesn't know any details of the database, doesn't know anything about AQL. You do not have to write any AQL in the application if you're going for Foxx. And you do not have to make any differentiation between single server or cluster inside the application, because that could all be abstracted away inside the Foxx service for you. Furthermore, you get increased security. You have fine-grained access rights management. And this is especially important if you are coming from a country like me in Germany, where you have really high regulations on the rights management, or if you're coming from a healthcare sector and so on, you actually have like a lot of laws that enforce you to keep the data as private as possible. And where you have very complex patterns, which user is allowed to see which information. And with Foxx, you just have a programming language, JavaScript at hand. Just write down all the rules in programming, so switch cases, for example, which are pretty easy to formulate. And then give the user access to full collections, some documents, or even just access to certain attribute levels. And patterns like, if this or that is stored in the document, then the user can read it or not, are actually possible with using Foxx, and which are pretty much impossible with a user rights management implemented in a typical database, because that is super hard to formulate in a general pattern. Foxx has a certain file structure that it needs to work, and the heart of the Foxx application is always a Manifest.json file, which contains all the meta information and all the install information that we need in ArangoDB to actually get this Foxx up and running. Then you have controller files or router files, which just define, okay, which routes I want to expose and what is the logic that should happen whenever these routes are called. So they define the HTTP API and the callback functions. Furthermore, you have static files, which can be anything. So for example, images, HTML, JavaScript, CSS. And by that, you can serve an administration frontend, because if you just serve an HTML file pointing to a JavaScript file with pointing to another CSS file, you actually got a website running. And this can talk again to the Foxx application that you have. Last but not least, you have scripts, and scripts can be executed at a certain event. So either you define them yourselves and you just say on this or that event, please run this or that script. And there are 2 predefined events, setup and shutdown. Setup is typically used to create the collections that you need in your service, adding some basic data that you need in there. And shutdown is to clean up the collections. So if you want to delete the sensitive data, or if you want to archive the data that you want to keep for further usage in your applications that you do not want to lose at all when removing the Foxx application. So let's talk about the Manifest.json and how this looks like. So Manifest.json contains all the meta information of an app, namely the version, description, the author who has written the application, and everything else that you need, license and so on. So on the right-hand side, you see one example manifest that I have just generated with my ArangoDB instance. Furthermore, it is used to find all files necessary for the Foxx application. Basically, the main.js, which is the entry point, telling the Foxx application, okay, please load this and that router that you have. It tells about the static files that are served. It tells where Mocha test files are stored, which should be executed in the test command. And it can define an index.html, which is the main entry point of the web UI that you want to ship with the application. Finally, we have the router, which defines the HTTP API, which can handle authentication, and which is used to implement all the logic to access the data. On the right-hand side, again, you see a code example of a very simple router that just offers one GET functionality, which is down below. That defines a cursor, an AQL cursor, that just returns all the usernames that you have stored in a collection users. This router also has some annotations, so it defines what is the response looking like, has some annotations what is for documentation, so it is a list of users, and it is an array contains only string. Then you have a summary, which just is a more descriptive information about what is going on. Description is even longer, so you can just define what are the things that you want to return on this or that route. So what you get doing this thing, first of all, you have full data access. So I'm just executing an AQL in my route. All the actions are actually encapsulated in an additional transaction. So I can just start a new transaction, do certain things. And if something fails, this transaction is rollback automatically. And if I want to, I can just execute full-blown JavaScript traversals if the query mechanisms that I get with AQL are not enough. So here I can just code myself and define at each state of a graph query what should happen at which point. Furthermore, you get for free input parameter validation using HPJoy format, which just says, okay, for each input document that I have, the document has to contain 3 attributes, the name, an email, and a password, and the password needs to match this or that regex or whatever. I can all define that, and if I have defined so, whenever a user sends something which is malformed, the service will directly reject it and will not execute my code that I have written inside the function. And furthermore, you automatically get generated Swagger documentation for all the routes that you have implemented and annotated properly. And the Swagger documentation looks somehow like this screenshot. And I can also show it live to you. So let's go back to my ArangoDB instance. Here I'm going to the Services tab, which holds all the Foxx applications that I have. And I can just add another service. I have to say where the service has to be mounted. So this is a postfix that will be appended to the URL of ArangoDB. And by this URL, I can then just access this or that service. So let's say I want to mount it on test. And if I just have my ArangoDB hosted on HTTP localhost and the default port, then I would actually can use this URL to speak with the service that I have mounted under test. Now I have 4 options to install a service. So I can either use the ArangoDB store, where there are some shared services that are created by the community, where I can just click install and just get a predefined service. The idea is that we can just reuse services that are common. I can just give my own GitHub repository, where I just say, okay, this is where it is on GitHub, and the ArangoDB will just download the zip file and install the service that is stored in this repository. If I do not have a publicly available GitHub repository, I can just use the zip command and just zip it myself and throw it at the database. Or if I'm just starting, I can just let the database generate a service for me. And this is what I'm just doing. So my name is Michael. I'm the author of this service. This is my awesome service. And my service does awesome stuff. I have to define a license, which can just be a random string. So you can just define your own license there if you don't want to use an open source license. And to make things easier, the generator is actually able to create CRUD operations for given collections. So let's say I want to create a document collection, my test, which is encapsulated inside the service. And then I can just click generate, and this will just create a new service mounted on test called my awesome service. And it has already generated the Swagger documentation for me, having the typical CRUD endpoints, all for the collection my test. And the nice thing about Swagger is I can just live try it out in my browser. So I can just send the request to the server, and right now I will not get any response from the server, it's just empty. But I get the curl command that I have issued or the request URL, so I can just lively play around with the data to just code against this API. Or I can also just create new documents. So in the default version, it will just be something like this, where I just get an example of a body that the service would allow. And I can just change the parameters as I like, try it out. And then we'll just say, okay, I have stored this thing inside your database. And if I now go back to the get route, which just lists everything, I will just get this document back from the database, all generated. Just one last thing I would like to show. Foxx services have a development mode, which is pretty useful in single server when I'm on my local machine, because if I put a service into development mode, it will be reloaded from disk every time I ask it. And it will tell me where the files are stored. So I can just take this path and go into this folder. And there's just the generated code that my Foxx service has created for me. And here you will just find out that there is this routes, my test, which is just the code that I have shown you on the slides. A little bit more complicated because it does the complete CRUD and the complete documentation stuff, handles errors and all these things. But this is basically everything that was generated for you. So whenever you want to start with Foxx, this is a good place to go. And if I just would like to change something in here, it would be rendered live into the Foxx framework. So let's just go to the to the get route at the beginning, and let's enter something in the documentation here. Let's do it in the summary because that's easier to find. So I just write this file. I go back to my service, go back to the API, reload it, and now you see that list all my items foobar test is just changed without doing some database reboot or reinstalling the service or stuff. Good. So my presentation is over. Thank you very much. If you have questions, please feel free to add them to the chat. And now I'll try to answer all the questions that have arisen during my presentations. So first question, will the slides be available afterwards? I'm pretty sure they will, so I think I will upload them on SlideShare, but I have to check that with the management. I think so. So next question, asset support works across multiple collections. And what about collection key value store update as asset? Of course, you get that. So in ArangoDB, we do not distinguish the different data models from our query perspective. So all of them can be handled with the same query and therefore with the same transaction. And therefore you get asset transaction across collections, across graph features, and across key value updates as one asset operation. So next question, at what point exactly do you transition from a document store with minor joins to a full on-edge collection? So the rule of thumb pretty much is if you know how many steps you want to go, and this never changes, you're better off by using just document stores with joins. If you have like arbitrary many steps in between, or even do not know how many steps you want to go, and if most of the information is actually stored on the relation between the documents, then you should go for the graph engine, so using the edge collections. So next question, if I think that Foxx with the front end like Vue.js would be enough for an application so that you could get rid of Node.js backend server at all, that depends on the application. So this is not the way that we would recommend it because it doesn't scale endlessly. If you put a lot of logic into the Foxx application, that means the database will get your bottleneck. If you put only the data logic into the Foxx application and the business logic into Node.js or something, then you can scale both of them differently as you need. If you are just running like a small application where you just have like 100 users or something, then it's fine to just go with Foxx and the front end, because then it's pretty easy to write a prototype and to just figure out if everything works. So as a starting point, you could do. For a large scale application, it's not recommended to do so. So what visualization frameworks I can suggest to integrate with Foxx? Actually, I must admit that I don't know the so many visualization frameworks that you could connect to Foxx. So we have a visualization ourselves where you can just figure out what is going on in the database. But pretty much you would actually connect the visualization framework with the database, not specifically with Foxx. So I'm sorry, I cannot give a detailed answer there right now. So there were another few questions. So is there a way to visualize the results of the query in a graph visualizer? You can, right now you can do. So if you have an edge collection and you actually return the path, then it will be returned in a graph visualization format. I can just do it live. So just go to the collection and I will just create an edge collection, which we haven't covered yet in this talk. So edges, and let's just say vertices, and just insert key 1 into vertices, execute, insert key 2 into vertices, and then insert from vertices 2 to vertices 1 into edges. So this is now the specialty of edge collections. They have two special attributes, from and to, which define where the edge starts and where it points to. So just store this edge into the edge collection. And if I now go to my query view, I'm still already there, and just say for vertex edge path in one inbound step, starting at vertices 1, using edges, return path. So I have to return the path to make the visualizer aware that this is actually a graph. Then I will just get the graph visualization down here. So if I have a more complex result, then this will blow up, of course. The second question in there was, are you right that I can have only one collection to store edges per one graph? That is not true. You can group several edge collections into the same graph, because that was the idea of the graphs in total. So just to show you, if you go to the Graphs tab, where you can define the edge collections, there is this little plus, and if you click on it, you actually get the next edge collection that you can add to this graph, and so on. And if you want to do this with Arango Shell, it's also possible to add more than one collection in there. The last question in this block was a few words about Pregel. So we have integrated a Pregel framework written in C++ in the latest alpha release, which is available for download on our website. So if you're keen and you want to try it out, you can just go to the website and download the alpha release. It contains a Pregel implementation, and there should actually be the dev documentation for this Pregel thing. So if you take a look at this, please give us some feedback. So, okay, further questions if we support TypeScript or if it's just JavaScript. So the Foxx framework has to be in JavaScript, but you can just write down TypeScript and transpile it to JavaScript and then send it to the server. That would work. I'm not sure if there is already a TypeScript compiler included, but I think there might be, but I'm not aware of it right now, sorry. So, so are there some big enterprise clients using this in production? There are, but I'm not allowed to give any names. I'm sorry. So can you filter and make indices from arrays in different collections? So you can make indices on arrays, but you cannot make indices across collections. So one index is only based on one collection. But in a query, if you're using two collections, then it will figure out that both collections have an index and can use both indices for both parts of the queries. But you cannot do like join indices, which would only work if you join those two collections. Another question, can you use ArangoDB for small applications or only for clustered and large scale? ArangoDB supports both. So you can just run ArangoDB as a single instance in a small application, having the same feature set as the clustered installation. So what I have just shown you was my single server instance running on my laptop. There's no cluster inside. So you can just use it for small applications in a single small instance, of course. So follow up on Foxx. What can the Foxx execution environment not allow for? So are there standard libraries limitations in V8? So there are some limitations in V8. So we try to be as compatible as Node as possible, but we are not Node.js. So there are some changes that Node.js have done in the implementation of wrapping of V8, and we have done some changes to V8 for our needs. And therefore there's like a small gap of compatibility, but we try to have as many JavaScript frameworks in Foxx available as possible. So I'm sorry if I just skipped some questions because it's getting a bit unsorted in the chat already. So one last question. So ArangoDB was started as an in-memory database. Has this evolved, or is there still some limitations? In 3.1, which is the current released version, it is mostly memory. So there is still some limitation on the memory. If you wait for 3.2, which will be released very, very soon, then we will have an additional storage engine. And there you can actually have an upper limit of the memory that is used, and everything else will be written onto disk, and this memory limitation is never crossed by ArangoDB. So this is in the next major release that we are gonna send out soon. So atomic operations like $push, actually all AQL statements are executed in an ACID way. So basically they are atomic. So you can just mutate an array of subdocuments in AQL. Good. Time is over. Thank you very much for staying with me. I hope I could answer a lot of your queries, and I hope you liked the presentation. Have a nice day or evening, depending on which time zone you are in, and goodbye. Thank you very much. Just one more thing. If you would like to help and support us, please go to GitHub and give us GitHub stars, because this is one of our key KPIs that we need to actually get some revenue. Thank you very much.